We're here at the Hydraulics Laboratory of Colorado State University, where we've built a physical model of the dam and proposed spillway of Denver Water's Gross Reservoir Expansion project. Here at the Hydraulics Laboratory, we study physical phenomenon with flowing water. What we've designed is a large plexiglass structure. When the model's in operation, it looks just like a waterfall that you would find in nature. The water comes down at a very steep angle, hits the pool at the bottom of the waterfall, is very turbulent, and then flows downstream safely.
Denver Water completed Gross Dam in 1954 with the intention of expanding it in the future. Now, a little over 60 years later, we're following through with that plan by raising Gross Dam by 131 feet. That will allow us to store about 3 times more water in Gross Reservoir. That'll add resiliency and help with the imbalance in Denver Water's collection and water storage system. So as you look at the dam, the spillway is that channel right down the middle of the dam. When the water level gets high enough, the water enters the spillway and just flows right down the face of the dam into the channel below. When we raise the dam, the spillway will have a totally unique design. It'll be the tallest and steepest of its kind, and it'll have steps all the way down as opposed to the smooth surface that the spillway currently has. So that made it really important to build the scaled model of the spillway to make sure it's actually going to work.
The computer models that we have available to us today are very good at initial evaluations. However, they are not able to answer the specific questions of a design this complicated. This is also one of the most complex models we've ever constructed, and it was actually built like a piece of IKEA furniture. We had pallets of 480 pieces of plexiglass that were laser cut that were then used to put the model together.
It's important to understand the relationship between water flow and the geometry of the structure and to replicate the processes that the structure creates. If we get those wrong, then the structure won't perform as designed.
Here in the physical model, we use a lot of different types of instrumentation to evaluate the hydraulic conditions. On the chute itself, we're looking for low pressures up top. That creates small little bubbles that can actually implode and damage the concrete face of the dam itself. This area here, the horizontal portion where you have the change in slope from the actual spillway down to a horizontal to match the channel, is called the stilling basin. So we also have features in here that are called baffle blocks, and they're basically just like little wedge-shaped blocks that redirect the flow back toward the spillway itself. And it creates kind of a big washing machine effect in here that's churning the flow. And then it moves down into more clear water, which is good, and that means it's very safe and not at risk to damaging any structures downstream.
We've learned a lot of things through this modeling process. We've already made some pretty significant adjustments to the size and configuration of things, and we're already seeing a cost savings coming out of this effort.
And every project is unique, every client is different with the needs that they have, and our job is to be able to provide the best hydraulic solution for a given project that we possibly can.